Jnanam paramam dheyam. Knowledge is supreme.
So let us look at let A be m cross n, A tilde its row equivalent. So let us write, so we will write now onward R E F, that is for row equivalent form, and R E F will be reduced R E F. Now R E F is already defined, so it is a new command, okay, R E F. So let us look at A tilde to be the reduced row equivalent form. So it is characterized, what are the characteristics? What are the characteristics of this? There is a number R, okay. So this is m cross n, there is a number R between 1 and the minimum. Once again I am going to the, okay, and there are numbers P1, P2, PR, right, as many as, okay. So there exists this such that the matrix looks like R1, R, and 0, 0 everything. So this is m cross n. So how many zeros will be there? These are m minus r rows are all 0. What does the row 1 look like? So row 1, that looks like 0, 1 and something, right, and similarly the other. So let us write R I. So this is P ith column. Pivot should be 1, right, reduced row equivalent form, right, and in the column CPI, so CPI column, all entries are 0 except other than which one? Ith column, okay. So what is, so entry what shall we call it, for in the column let us C I j equal to 0 for j not equal to P I. Means the column looks like this. Let us just write that. So this is the column CPI, it is 0 here, 0, 1, 0, 0, and what is this place? This is the ith, right, this is the ith entry in that. Ith row is non-zero, we are describing the non-zero rows. So the ith row is non-zero, the non-zero entry is, first non-zero entry is 1, everything else is equal to 0. So let us give this R a name. So let us put a definition. The number R is called the rank of the matrix. So what is R? R is the number which is coming as the non-zero rows. R rows are non-zero in the reduced row equivalent form of the matrix, right. So, that number r is called the rank of the matrix, right. R is called the rank of the matrix. So, now let us see. So, let us try to apply it to a system of equations. What does it mean in the new terminology, right. So, consider a m cross n system of linear equations so that is a x equal to b. So, the m equations in n variables, right. So, a is m cross n, okay. What is x? That is the variables, right. So, x 1 x n, let us write that. So, that is n rows and 1 column, right. And what is b? B is the vector coming on the right hand side, constants. So, we saw that. So, what is b equal to? B 1 up to b m, right, m equations. So, that is m cross 1. So, m cross n multiplied by n cross 1 is equal to m cross 1, A x is equal to b, that is a matrix notation for a system of linear equations, right. And how did we said we will see whether a solution exists or not. So, we said we will look at the matrix A and B, that is augmented matrix, we said we will look at that, right, and reduce A to row echelon form or reduced row echelon form. Okay. So, when you do that, this will become A tilde and this will become B tilde, where A tilde is the reduced row echelon form of the matrix, right. Okay. So, A tilde reduced row echelon form of A. Okay. And we said the system is inconsistent if what happens? If there is a row in the part of A which is 0 and there is a non-zero constant coming in B, right. Now, in terms of if I look at the bigger matrix A and B, A has already been reduced to row echelon form or reduced row echelon form, and B has changed to something. So, if I look at the bigger matrix A tilde B tilde compared to A B, then the rank, the number of non-zero rows in A will be strictly less than the number of non-zero rows in the bigger one, if it is a 0 here and a non-zero there in B. Clear to everybody? Yes or no? So, the matrix A tilde B tilde will look at it is 0 here and some non-zero entry coming here, some B r tilde, let us say, right. So, this is the rth. See, okay. This is a non-zero entry here. So, that part is of A, that is A tilde, bottom rows are all 0 in it, right, somewhere non-zero. So, in the but in the 0 thing in B, something non-zero is coming in that column of the corresponding to B. If a non-zero comes, that means you have got an equation like 0 equal to non-zero, right. But look, interpret this in terms of the rank. Rank of A is this much, but the rank of the bigger one, there is a non-zero entry here. So, it will be bigger than the rank of A, because there is number of non-zero rows is at least one more, that inconsistent equation, right. So, we write this as that system is inconsistent if rank of A is strictly less than rank of A B. So, we are writing that result in terms of the rank now. Okay. So, that is one. Unique solution, when was the system having unique solution? R is equal to n, and that should also be equal to rank of A B, right. Consistent only when the ranks are same, otherwise inconsistent, right. So, when consistent and rank is equal, solution exists and there is only one solution possible. And the third, R equal to rank A, which is also equal to rank A B, system is still consistent, but this is strictly less than n, it is strictly less than n, right. So, then there are infinite solutions, then there are. So, this result is interpreted in terms of the rank, right. And how do you get those infinite solutions? The variables. So, one makes a convention that the pivotal variables will be computed in terms of the non-pivotal variables in an equation, right. Somewhere pivot is coming, that is corresponding to the variable, and that gives a relation that is equal to something, right. So, in that you have to give arbitrary values to some variables to compute one in terms of the other. So, what you do? You always compute the pivotal variable by giving arbitrary values to the non-pivotal variables, right. Compute in terms of them. So, that is a convention, because we have to give it to a machine. We can't say randomly you do compute whichever you like, give whatever arbitrary value you like. So, for the definiteness, we say that whenever the number of solutions is infinite, right, that means there are n minus r variables which are going to get arbitrary values. R is the rank of the matrix A, n is the number of variables. So, n minus r variables are going to get arbitrary values. So, we give those arbitrary values to non-pivotal variables, and the pivotal variables are computed in terms of non-pivotal variables to get all possible solutions. And later on we will see this also has some other usefulness when we want to describe the solution space. We want to describe also infinite solutions in some finite number of them. So, we will look at what is called the basis of the solution space. So, this will be useful there and then. So, this rule will be useful there. So, we will see examples next time of this. Okay.